Okay, we're ready. Let's go live. All
Yeah,
right.
let's do it.
I think we're good.
Mhm.
Hello, everyone. Welcome to today's brand new episode of Corecast. I'm your host, Tim.
I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Queercast. We're back after maybe 2 weeks or so, or 3 weeks. I lost track, but we're ready to start a new series. The last time we were talking about all topics related to time, and we thought it was time to move on to another topic. So yeah, a few logistical things. If you haven't already, do join our Discord channel. You can ask us questions there. And if you're watching on YouTube, where we try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we get to them as well. So for further ado, let's get to it. So we were talking about essentially how to break the laws of physics, if I heard that correctly. And so, Mikey, you look very eager. How do I break the laws of physics? Some laws I don't like entropy increasing, I don't like. What do I do about that? How do I get
I think the
around
thing
that?
I think the thing to realize about the laws of physics, and this is kind of the point of this episode, like people often think about the laws of physics as though they're like immutable laws that can never be violated. But like for practicing physicists, like if you're a fundamental physicist, um, uh, one of the key facts about the laws of physics is that each one has like a certain regime of validity. There's no laws of physics that we know about that, well, I don't know. I guess it's a little bit strong to say, but we expect all laws of physics to break down at a certain point. Typically, as you get smaller and smaller and smaller, we assume that the laws of physics we currently understand probably, don't hold up at a certain point. And so whenever I hear articles about like, oh, like Isaac Newton was wrong, or Einstein was proven wrong, it just kind of grinds my gears a little bit because you have to understand that like even though Newton's laws were supplanted by Einstein's laws, it doesn't mean that Newton's laws were wrong. It just means that Newton's laws have a certain like regime in which they're valid.
So, Mikey, one thing you mentioned that I want to make sure I understand. You mentioned as things get smaller and smaller. What about if things get larger and larger? Kind of like the example that comes to mind is like you had Newtonian mechanics, and then that had some simple picture of gravity, but if you zoom out large enough, the picture of gravity is very different. Is that fair to say? Or
Yeah. Yeah. Mhm.
so
And
couldn't it apply the other way is my question as well. You go larger and larger.
yeah, the other way is not as well understood.
Mhm.
There's certainly as you go to larger and larger distance scales, you start to see the effects of general relativity, particularly in the expansion of space-time. Um, yeah, I don't know, Tim, you want to handle that?
Yeah, I mean, I would imagine as we zoom out, we start looking at the macroscopic structure of the universe, and maybe even go to the realms of multiverses. And certainly, a lot of the physical laws don't take that into account, and there's no reason to, right? Like what's happening on Earth, we don't need to care about what the multiverse is doing. So to some extent, physics is designed to be practical, and because physics has to match up with experiment, and experiments are usually testing a limited regime of data, or there's a limited window of opportunity for testing things. That's why the laws of physics also tend to have a limited regime of validity. I think it's foolish to assume that whatever mathematical equations we cook up somehow will be valid to infinity, right? From infinitely small to infinitely large. I think that's unreasonable.
Yeah, that's a fair statement. I guess to make this discussion a bit more concrete, can you give like maybe certain examples that you would encounter in like a high school physics class, for instance, either Tim or Mikey?
Yeah, probably the simplest example where we understand how physics from one regime changes to another regime. Let's say we can talk about the phenomena of sound waves, for example, right? Like, the reason why you our listener, or you and I are hearing this podcast is because of sound waves in the air, one way or another. And of course, we can use physics to describe, we can have some wave equation to describe the motions of the collective air molecules moving in and out, and ultimately hitting our eardrums, and then we hear these words that are uttered, right? So this is the kind of the theory of sound waves. But you can't really use the theory of sound waves to describe, let's say, microscopic movement of the air molecules, right? Because the equations just don't accommodate that. So we know the sound wave approximation will have to break down to some regime. For example, if you zoom into really small, you look at individual air molecules, that, the wave equation will probably break down. Or if some objects move at really fast speed beyond the speed of sound, some of the basic equation could also break down as well. So these are just examples, and we know how those theories will have to be modified because we know what air molecules is made of. So this is a good example.
Gotcha. Mikey, are there any other examples you want to throw in that you like personally?
Yeah, I think the classic examples also like, classical laws of physics, the idea that, so as Tim mentioned, at very large distances, you can describe things like water or sound as waves. When you zoom in, you can kind of imagine these things as little billiard balls or little hard little particles. And there's nothing wrong with the sound wave description per se. If you have predictions based on this wave model and this based on this billiard ball model, they better agree in the regime where both are valid descriptions. But even when you zoom even further than that, you find that this picture of little hard like particles bouncing around, that breaks down. You start to see the effects of quantum mechanics arise, and so like it's basically a process of generalizing the description. Physics progresses through a process of generalization. It's never like one theory is wrong and is replaced by another. So that's kind of what we're raging against.
Yeah, so that's an interesting point where you mentioned that like if you want to describe like individual molecules bumping into each other, the theory of sound waves won't work. What about the other way around? Like what if you took the theory of like particles bouncing around and you wanted to get back like a theory of waves, for instance? Does the other way work better? Or is it a discontinuous jump? Like how does it look going the other way?
I think the directions are not symmetrical, because from the theory of molecules, you could, in principle, let's say you can run simulation, derive the theory of sound waves. But the other way around, there will be multiple choices now. For example, we know that different air molecules, like nitrogen and oxygen, probably will produce sound waves as well, right? So you can argue that there are multiple theories of air. Air could be made of nitrogen mostly, or maybe made of oxygen, right? And then those will both produce sound waves. So if you just have a theory of sound waves, you can't really figure out what the composition of the air is. So going backward, there's almost more and more ambiguity as you zoom out, because one can be derived from the other, but not the other way around. I don't know if that makes sense.
Yeah, there are always multiple microscopic descriptions that are equivalent to any macroscopic description.
That is a fair point. Oh, Tim, were you going to say something? Or
yeah, I was going to say I think this viewpoint of physics is kind of like the way physicists view physics is kind of like a web of theories, one linked to the other, and there's kind of relationship between them. Like, for example, the theory of sound waves is the macroscopic counterpart to the theory of molecules, and so on and so forth. And there are many of these relationships. And this is contrary to a lot of public perception. People think that, there's only one theory, the theory of everything, that everything should be derived. While you can think of that as kind of maybe, I don't know, like a romanticized view of science, like maybe in principle that's true, or theoretically that's true, but in practice, it's really not how it works. So when people say, oh, we discover some new physics, it doesn't mean that this web of theories we just completely throw it away as if like, oh, something new completely takes over. It's more like, hey, we add another layer in this map of theories, in this space of theories, and there's more relationship between theories that we discover. So it's more like how do I put this? It's more like, you know how like jigsaw puzzle, right? It's like you're putting one more piece of the puzzle in as opposed to like tossing the entire jigsaw puzzle away and just start from scratch. I guess that's the more proper viewpoint, I think.
So I guess okay, I'm gonna come from a reductionist perspective. I'm curious to get your guys' take on this. What like what's so difficult if I had like a theory that describes like, small enough scale of things. Let's say I had that. And then I take like the limit as like the number of small things I have like grows to infinity or like grows just, some like and take like a mathematical limit and say, okay, it'll approach this sort of behavior at this scale and then at this scale. Like, what is kind of like, I guess, stopping us from doing that if I were to ask like very naively?
There's nothing stopping us from doing that. That's how physics progresses, right? So we do exactly this exercise, right? Um, and usually, if you take a theory and you push it to its extremes,
Mhm.
and this isn't a principle, but or something that has to happen, but it's just something that's happened over and over again in history. Is that when you take your a certain description of nature, and let's say you ask the question, what happens if I just look at this theory in extremely short distances? um, you might start to notice some peculiarities. For
Hmm.
example, you might know that um, if you have an electric charge, the energy you feel as you get closer to it goes like 1/r. So the closer you get to it, the larger the magnitude of energy you feel. Um, but according to that theory, when you get extremely close to the electron, the energy blows up to infinity. And that looks a little weird. That's kind of become known to us as some kind of indication that the description is stopping making sense in this regime. And
Mhm.
so, what's the solution to that? This is where kind of the interplay between theoretical and experimental physics comes in, because there are multiple different microscopic explanations for every macroscopic description. You actually have to look and see which one is true.
Hmm. Makes sense.
Yeah,
Makes sense.
yeah, and I will add that to Sahil, to your point. Like, yeah, physicists do try yeah, exactly what Mikey said. Do try the approach to kind of take things to the extreme to try to really find things out. And this is where a lot of these infinities come from. Like when you run simulations or you do calculations, when you push some numerical numbers to the extreme, you start getting nonsensical answer. And if you look at a lot of popular science or if you're not familiar with these issues, you might get very confused. You're like, oh, holy crap, physics is wrong now. Physics is completely nonsense, But in some sense, that's kind of like a feature, not a bug, if you like to put it that way. Like like the laws of physics, um, you were not supposed to push it to its extreme. Like it's built into the
Mhm.
theory that there's some limit where you can push it. So when you push the theory too much, I mean it breaks. It gives you nonsensical answer. But that doesn't mean that those nonsensical answers are actually nonsensical, right? Because in the real world, you can go ahead and measure them,
Mhm.
and there exists no instrument that can measure infinity, as far as I know. So nonsensical answers do not exist. It merely indicates a theory has been pushed past its limits, right? But then that's interesting now because when that happens, that means we could discover new physics. So it's like a feature, not a bug, I would say.
Mhm. Well, okay, what if I take maybe this is taking us off track. Let me know if this is taking us way off track. But like, what if I take like the theory of quantum mechanics and I try to see can I reproduce like the classical mechanics, the everyday thing that I'm used to, like for instance, this laptop in front of me, just using like quantum mechanics, just like throwing bajillion particles together and just doing it like that. That like, I mean, does that necessarily break quantum mechanics, or just want to get your thoughts on that?
Well, you mean you're talking about like using the microscopic description in a
Ye-
macroscopic way?
yeah. Like if I just take all these microscopic descriptions and just put a bajillion of them together and then try to reproduce what I see macroscopically, is that like breaking the microscopic description? Like if I can't do it because it's intractable on a computer, does that mean like it's a wrong microscopic description of the macroscopic phenomenon?
I would say that's like a consistency check, right? So if
Hmm.
you have some idea of what the microscopic physics look like,
Hmm.
one way to test whether or not it's true or not is to zoom out. And
Hmm.
when you zoom out, that microscopic description better agree with everything else that you know that occurs in macroscopic distances. Like one way to test whether quantum mechanics is correct or not correct, so to speak, is to zoom out and see whether or not it reproduces Newton's laws or classical electromagnetism laws. And if
Hmm.
it doesn't, then you can be damn sure that quantum mechanics is, probably not a viable theory. But luckily for us, when you actually do zoom out and you use quantum mechanics to describe macroscopic things, you do get perfect agreement with everything else figuring out.
Yeah, let me just add that although for practical purposes, we don't literally throw all the particles and do quantum mechanical calculation because that would take way too much computer. What happened is that people try to reproduce this web of theories, right? So you can take quantum physics and you can zoom out and derive equations of, let's say, classical physics. Then you say that, hey, look, um, from quantum physics, you outcomes classical physics, so one can derive to the other, and that's enough. You don't really need to run simulations to confirm that, because theoretically you can derive a more coarse-grained equation. Let's put it that way, like a more simplified, zoom out version of the equations, and that's enough to show that the smaller theory kind of reproduces the larger theory, and that's basically done, in physics, in chemistry, and probably also in biology to some extent.
Hmm. That makes sense. One other question I had is like, so you talked about this web of theories. Like on one side you have fundamental physics web of theories, and on the other, I mean, maybe it's not two-sided. There might be more sides, but at least in my mind, then there's all the condensed matter theories. And so, like, is there? And it's okay if you guys don't know the answer, but is there a linkage between that? Because when I was looking at like condensed matter, you have these like models that seem how should I say, don't seem like very realistic in terms of what the particles are actually doing, but they describe macroscopic properties they observe, like temperature, electroconductance, and like various other things. But the mechanism in which the model works, or the interpretation you give to the model, doesn't seem very like as realistic. Electrons hopping on like a lattice site, for instance. Like I don't believe electrons are actually hopping on like from lattice side to lattice side, as an example. But it works that way. It happens to work that way. Or it's kind of like you, as a theorist, come up with a model and then you hope
Yeah,
they find a material that actually matches that.
yeah.
So I'm wondering, like, from that perspective, yeah.
I would say this is the art of, kind of filling in the blanks in this web of theories, right? Like condensed matter, you can argue that entirely is the study of emergent phenomenon. Like we know that
Mhm.
all the materials, at the end of the day, if you throw it in an accelerator, break them all down, it's just going to be protons and neutrons and electrons. That fact is absolutely true, right? You can
Mhm.
take any hunk of exotic material, just
Mhm.
bombard it with particles. That's what you find. But the interesting thing is that um, from quantum physics, when you zoom out, you don't necessarily just get one type of simple laws. In some extraordinary circumstances, like if you arrange molecules in a very particular way, you can get interesting behavior, like superconductors, which is on the news recently, but we won't talk about that. Things like superfluid and insulator, conductors, semiconductors, with all kinds of interesting behaviors, and you can argue that this is kind of the study of these web of theories, right? Like you have quantum physics on the one hand, and it spawns all these little theories, these models of, different materials, and they map onto our experience for these materials. You can argue that on the one hand, this is kind of a confirmation, the fact that this paradigm has worked so well so far. It's a proof that this paradigm of web of theories is working, right? Like this is how science works. So,
Sahil, how come you don't think electrons hop? Electrons hop.
I don't know. I feel like I don't know if I would describe it as like they like discreetly hop, for instance. I don't know.
yeah,
Well, if you assume that they hop, then you get the right answer. So
yeah.
Yeah.
Sometimes it's not so important to get the assumptions right, because in these web of relations, sometimes you get what we call universality, universal behavior. Like even the assumptions are somewhat off, you somehow capture most of the essence of it, and your conclusions still come out mostly right. Like you can just adjust a few numbers and get it more right than wrong. And this is kind of the art of, weaving this web to some extent.
Yeah, actually, another example I would give, maybe electron hopping wasn't necessarily the best example, but like if you take like two-dimensional materials, you can, I think for certain materials, actually get particles that don't exist in 3 dimensions, so-called anions or something like that.
yeah.
And so I'm wondering, like, I guess, is that part of the filling in the gap thing, Tim, as you were mentioning?
Yeah, I would say so. This gap is just, there's still a lot of interesting things that can be accommodated, right? And you can argue, this is kind of the law of, how to put this? I'm not a big fan of using this word, but this is the law of complexity, right? Imagine you make a comparison to language. In English we have what 26 symbols, alphabets, right, to make up words. And in the beginning, you only have 26 alphabets. It seems like it's pretty useless as a language. What can you do with 26 alphabets? But when you combine them in different ways, you can form words, and you can combine these words to form meaning. And these meaning can capture abstract thought, like physics, right? So it's sort of analogous to how you start with a few particles with simple laws, but different combinations of how large some interactions are versus some other gives you this huge complexity, and then this complexity creates very interesting phenomenon. And that's that's the study of a lot of physics and physical science we have.
Yeah, the Anion one is actually interesting. It's an interesting example because yeah, that's something that we haven't even talked about yet. But like, because we've been talking about regime almost like exclusively now in terms of distance scales, right? Like laws of physics change as you zoom in or zoom out, right? But yeah, that's an interesting example because like if you look at the laws of physics like in 3 dimensions, right, and you collapse one dimension down to like a surface, you get these weird predictions that you can have particles that can have like 1/4 spin or 1/3 spin as opposed to the normal like 1/2. And then so that there's something you can test. Like you can sort of design an experiment just on the surface of a table, right? And you can see if these theories hold up, if you can actually make these kinds of like exotic predictions come true. And it turns out that you can. Like people can observe the behavior of these like kind of seemingly fictitious particles, but in experiments. And to me, that kind of breathes reality into them. So yeah, it's a little weird.
But I would say we have to keep in mind that these are approximate. Like these theories have a limited regime of validity. For example, if you just grab, let's say, a particle beam and start blasting these materials, let's say a superconductor or some of these material with exotic properties, they're all gonna self-destruct basically. They're all gonna break down back to electrons, protons, and neutrons. And a lot of these material only exhibit interesting properties when, let's say, when you zoom out long enough and you don't have, let's say, enough thermal energy to disrupt them. many of them only occur in a low. That's one of the reasons why these interesting behavior only exist at lower temperatures, or at least have tendency to exist at lower temperature. So yeah, so once again, these are what I would say like emergent phenomenon, basically, which encompasses a large fraction of physics. I mean, we're saying, we're by no means diminishing these areas of research. I mean, that's how physics is. So.
Mhm. I guess like so one question that I have is like you have these like different theories in this web of theories that apply at different regimes, like at very small scales. I'm just simplifying this, of course, at very small scales, you use quantum mechanics, and maybe at medium-sized scales, you use classical, and then maybe at like super large scale, you use general relativity or where there's strong gravity and such like that. But I guess like how do you know which one to choose to use? Like because the boundaries it's not really there. It's not like a hard boundary where nature is like, okay, if we go below this limit, apply quantum mechanics. If we're above this limit, apply other theories. Or if we're in this material, apply this. So kind of like how do you guys sort of think about that?
I think I think generally speaking, like the way it's gone, and this is kind of like a I don't know, maybe more of a stroke of luck than anything. But sort of like the dogma is that the microscopic theory is always more general than the macroscopic theory. So if you have a
Hmm.
theory of like very, very short distances, let's say like a quantum mechanical theory of quarks and electrons, um, it seems to be that those are more all encompassing.
Hmm.
So this is where the idea of like the so-called theory of everything comes from. There used to be a popular belief that if you could understand what theory of physics is true at the very, very, very shortest distances, then that would be a proper, robust description of everything in the universe. We're not so sure about that anymore. It seems like that
Hmm.
might be a little bit of a naive viewpoint at this point. But for the last 300 years, consistently, we've seen this to be true, and it's been kind of like a guiding light in theoretical development.
Yeah, I would add that from a practical perspective, like which law to choose, what regime to choose. I think you can take a very pragmatic experimental approach to this. Like for example, let's say we want to study, I don't know, interaction of quarks and electrons, whatever. Let's say at energy in the X-ray or gamma ray regime, right? Let's say we want to do that. Well, we know that many of the properties of these particles have been measured to great precision around these energies, right? So I can then I should use the theory where these experiments have supported and extrapolate a little further. Maybe like, another 1,000 times more energy. I can use the same theory to extrapolate it, right?
Hmm.
And that's what people have done. You take a little small leap of faith to say that, hey, these theories have been tested at this energy, then it makes sense to extrapolate to just a little more, to take a small leap of faith. And so I would say, yeah, and that's how it works. Like when we studying black holes, we always have to double check kind of like which regime is valid and what theories we should apply. And in some sense, physicists always work with these emergent theories. Like we don't have a theory of everything. Everything we study, from black holes to particle physics, you can argue that these theories are all emergent from something more fundamental. And you always have to pick and choose, and make sure that your theory is valid, and your theory makes sense, and also that it makes sense in the range of validity that your experiment is comparing to. And I think that's the nuance that's often missed, when people talk about physics and doing research and all that.
That said,
Yeah.
we'd be lying if we didn't say that like the goal of for us as particle physics physicists is to find the theory that has the largest regime of validity, right? Like the goal is in a sense is to find the theory that is true in the widest variety of circumstances.
Hmm. I see. I see. I guess then like to kind of take a step back and look at this like web of theories and how you transition from one to the other and this concept of like I don't know if we call it a regime change or like just changing of like what regime you're working in. How would you sort of like conceptualize that? Is that more of like if the environment in which you're like doing the experiment in changes? So for instance, like a material has a very different type of environment than like, than if I do a particle physics experiment, or like, the environment of the early universe, like really, really early universe is very different than like what it is today, for instance. So is that sort of how I can think about it? Or like, how do I think about it physically more than like just a parameter like energy or like other quantities like number of dimensions? How can I like, make it more concrete?
No, I think that's absolutely true. Yeah, the environment the
Mhm,
physical system is in,
mhm,
sometimes is one of the parameters that dictate what laws of physics you should use, right?
mhm,
Like in the early universe, when the density is really high, the temperature is really high, you have to
mhm,
use quantum theories because density is so high. But you also, because the temperature is also high, it also makes sense to use statistical physics. So you kind of have to,
mhm,
how do I put this? Like every investigation in physics is kind of like a little battle, and you better choose your weapons wisely in order to do the proper calculation. There's never I guess and sometimes there could be multiple right answer. There isn't just one way to do a calculation. There are multiple ways to do it, and for the theories to be correct, these multiple ways of doing it should yield the same result, or at least the same result when we are within the regime of validity.
mhm. What one question, I guess, Mikey, do you have anything to say to that, or
Oh,
before
no.
I ask my next question?
Yeah.
Oh,
Oh,
did you
no.
were you
Yeah.
gonna say something? Okay.
No.
So Tim, you were talking about like, oh, if you spot infinities in your theory, it means that something is wrong. Are there other ways to know that your theory is wrong besides infinity? Like the concept of like the sound waves and individual particles bumping into each other. Like if I just, go headstrong and just apply a theory of waves to particles bouncing with each other, maybe by modeling as like, they're like the interaction between them as a wave, like itself, like a miniature, smaller size wave. What would be the issue with that? Like, why is that wrong? Or I
Yeah,
just I
so
just want to gauge, like, yeah.
yeah, so sometimes it's not just infinity. So of course, when a theory yields infinity, something is messed up, right? Something is wrong.
Hmm.
But
Hmm.
sometimes there could also be inconsistencies, right? Like I mentioned, because sometimes in the same within one regime of physics, there could be multiple theories that could give you the right answer. But
Hmm.
then sometimes it could happen that the answers are not the same. Like let's say let's say in the example of sound waves,
Hmm.
maybe in the regime where you're not zooming in too much, so
Hmm.
there's still sound waves around, but then
Hmm.
but you can already kind of see particles. You might be able to calculate, let's say, I don't know, the speed of sound, or how sound waves propagate in these two limits. Maybe by first simulating how particles move on a computer, and then versus working these you know mathematical equations of sound waves and see how they propagate and see if they match up, right? And
Hmm.
sometimes you might find that they don't match up, right? And then there's a bit of a conundrum, which one's right in this tug of war. Did you miss something? What was the derivation not correct in some ways? So so I don't know what would go wrong in this example of sound waves. um that's unclear to me at this moment, but probably there will be some inconsistency if you try to push too far.
Hmm. Hmm. Are there any examples from like other branches of physics where you can think about not an infinity but an inconsistency?
Hard to say. There's not a whole lot of branches of physics whose goal is to find like a generalized description. It is kind of like that is kind of like the realm of particle physics.
Hmm.
And in particle physics, it is like, I don't know, there could be various ways in which like the inconsistency of a theory might manifest, but the presence of infinities is definitely our favorite one.
Yeah. Yeah, I mean, I would say we talk a lot about black holes. I mean, that's one of the prime examples, right? Like, if a black hole is large enough, you would imagine Einstein's theory should be roughly correct. And then there was a debate on, there's a theorem from Einstein's theory of relativity that says that black holes has no features on the surface of the horizon, meaning that black holes they don't contain very much information, right? But then you have the quantum theory of black holes that says, well, information cannot be destroyed. So if something falls through the event horizon, because from the outside you never see the object fall, whatever the information that exists from the object must be stuck on the surface of the black hole. But then there's a little bit of inconsistency now, because Einstein's theory says that, well, too bad. Things cannot be stuck on the surface of a black hole. There's this thing called the no-hair theorem for black holes, right? So this is one example, inconsistency. But like, hey, look, we expect both theories to be somewhat appropriate in the analysis. But there's some inconsistency, and then you place your bets. Be like, hey, which one do you think it's more right? Which one do you think is more wrong? But and there are quite a few inconsistencies actually in the particle physics frontier when these things happen. So quantum gravity is one of them, but there are a few others, I think.
Yeah, I remember Leonard Susskind. He said multiple times in many lectures that, like, when there's two things that seem inconsistent with each other, there's like something there. Like, that's the direction you want to go in. Anyway, yeah, that reminded me of that quote. What's up, Mikey? Were you gonna say something? Or
Yeah, I was gonna mention, yeah, like it's interesting. Like I was talking to like a coworker about this, and I think people are surprised that like the goal of physics is to break physics, right? That's how you make progress. Like if you do an experiment and it just shows you what you already know is true, that's like the most disappointing thing, that can possibly happen. Physics progresses through this kind of like process of breaking the theory and then finding out how to fix it, and then figuring out where it breaks, and then figuring out how to fix it. So yeah, as Tim said, I guess this is just, yeah, when Tim said it's a feature, not a bug. It's like the thing that enables progress.
yeah. So we're almost at time, and I want to give you guys a chance to leave any concluding thoughts with the viewers. Mikey, your thing sounded perfect for a concluding thought, but I don't know if you wanted to add more things on top of that.
Yeah. The only thing I'd add is like, I think the modern viewpoint is like the laws of physics are descriptions of nature, right? And there's no rule that says that a description of nature has to be unique. But the goal is to find a description that is as valid as possible in the widest, most diverse range of situations. And the way we do that in practice is by examining the places where the theory seems to break down. This is why black holes are such a topic of interest, because those are the most extreme theoretical environments in the universe. And so the belief is that if you understand how physics works in the most extreme of situations, you're going to come out of that with a description that is as widely encompassing as possible.
Yeah, and I'll add to that there's a common saying that laws are meant to be broken, and I think that applies to physics as well. There hasn't. I think all the physics theories that have existed, there exists. Even within the physics theory itself, there's an implicit regime of validity. Every single theory. So even within the theory itself, we know at some point it's going to break. And that's no question. And of course, if we break sooner than that, people are happy because there's something new. So I would just say, just say, a lot of times you see popular science article that says, hey, the laws of physics is broken. Einstein was wrong, Newton was wrong, and then all of a sudden we have to completely change our perception of the reality. No. That's not even close to true, right? We have a web of theories, and if something is wrong, we add a new understanding. This web just get bigger and bigger, and our understanding becomes more complete. So I would say, don't be alarmed by laws of physics getting broken. It's a feature, and it doesn't mean that we throw our worldview completely away. It means that we just, have a few amendments to make our worldview more comprehensive. So that's kind of the more modern view of physics, I would say.
Gotcha. Yeah, that sounds great for concluding thoughts. But okay, so we have a last minute question, which is a little bit more technical. I probably want to, I'll give you guys a chance to answer this, but it might be a bit technical, but have a stab at it. So he says, "Hey guys, what exactly does it mean that quantizing gravity doesn't work because it's not renormalizable? In mathematics terms, what does that really mean?" That
Yeah,
was completely off the wall question.
yeah. I think
But
we can't answer that right now. It's gonna take a
okay.
long time. I mean, it has to do with how these inconsistency arises. How do we deal
Mhm.
with it mathematically? So that could be a topic for our next episode. But this
We should promise the user that we'll address that in the next episode.
we will address that. Maybe not in the next episode, because it's a very kind of convoluted topic. But we will address
We
it.
should find a way. We should try our best to answer these questions. And if since it was thrown out right at the end and there's no time, we should let's find a way to work it in.
Okay. So to the audience member who asked that question, we will do our best to answer it next time.
We will break physics. Let's do it.
Yeah, to answer this question for you. Okay. All right. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
All right.